Photodynamic therapy, or PDT, is a cancer treatment based on the interaction of light, a photosensitizing drug, and oxygen. Depending on the part of the body being treated, the photosensitizing agent is either put into the bloodstream through a vein or put onto the skin. Over a certain amount of time, the drug is absorbed by the cancer cells. Then, light is applied to the area to be treated. The drug absorbs the energy from this radiation and initiates a photochemical reaction that kills the cells.
In this process, we first must go into the fundamental principles of the therapy. The therapy works by three main components: light, photosensitizing drug, and oxygen. Then, the cell is induced to death by various pathways: direct cytotoxic effects on tumor cells that produce death by necrosis or apoptosis, damage to the tumor vasculature, and induction of a robust inflammatory reaction that can lead to the development of systemic immunity. If we say that there is one component more important than others, we would say that it's a photosensitizing drug. But how exactly does the drug absorb the energy from the light in order to kill the cell?
Well, light absorption is due primarily to a few highly absorbing molecules including water, oxyhemoglobin, deoxyhemoglobin, melanin, and cytochromes. They are called chromophores. The electrons of these substances have the capacity to absorb the energy of the light and then get excited from their ground state to another much more energetic. The PS, almost exclusively used in the clinical PDT, is hematophorphylin derivative or substance derivative from HPD, named photoflin-2. Since that archetype photosensitizer is a photoflin, a complex mixture of many different photoflin molecular derived from blood. In the next table are the most common PS used in PDT. The PS in its ground state is characterized by a pair electron with a total spin and the corresponding spin multiplied by 1. This ground state configuration is termed by a singlet state. After appropriate light irradiation, the photosensitizer excited to an electronically excited singlet state. After a certain amount of time, the PS decays into a triplet excited state. Then here is when all begins. This state has a relatively short lifetime in biological tissue, typically tens of microseconds, and the excite via energy transfer, exciting to a ground state, molecular oxygen to a triplet state. If sufficient energy is provided in this transfer, singlet excited oxygen is produced. Unfortunately, the PS have some cons. Significant tissue penetration is achieved by a light at 630 to 635 nanometers, which corresponds to a weakest absorption of pH2. Moreover, a continuous accumulation of photoflin based to a photosensitizing drugs and their slow clearance from the skin leads to long-lasting skin photosensitivity, requiring one to avoid light from 4 to 6 weeks after photosensitization.
In contrast, lasers provide the exact selection of wavelengths and the precise application of light. The most useful are the pulsed lasers that produce brief light pulses of millisecond to nanosecond of duration. The introduction of lasers equipped with optical fiber revolutionized the PDT and expanded its applicability in medicine, enabling the endoscopic delivery of light to almost every side of the human body. The wavelength of light used for PDT is typically in the wavelength range of 600 to 800 nanometers, the so-called therapeutic window. In this wavelength range, the energy of each photon is enough, 1.5 electron volts, to excite the photosensitizer, and yet low enough so that the light has sufficient penetration into the tissue.
There exist four main types of light-tissue interactions. We have reflection, absorption, scattering, and transmission. Reflection and refraction can be perfectly described by Snell's law, where we have a fast medium and a slow medium. So here we have our light beam. We can see that part of the light will be absorbed, part of it will be transmitted, scattered, and a reflection. Absorption in tissues is relatively straightforward. It can be described by the Berberan-Santos law, which is I is equal to I naught times E to the minus epsilon times C to the L. But this law can only be correct under the following assumptions. First of all, absorption compounds are independent. Concentrations of observer is constant along the light path. And atomic effects such as multiphoton absorption, optical saturation, or stimulated emission can be ignored. Unfortunately, this equation is not accurately enough because, as we can see, tissues are turbid media, so we will have to find another equation that better describes the interactions of light and tissue.
Now, let's talk about the physical process of absorption of energy in atoms and molecules due to light. We can study the structure and properties of molecules by examining the radiation they emit or absorb. The energy of the molecule can be divided into four categories: electronic energy, translational energy, rotational energy, and vibrational energy. We can say that the total energy of a molecule is determined by the sum of all these energies. Normally, the molecule would take on the configuration with lowest energy, in this case the one designated by the quantum numbers L equals to 0 and B equals to 0. External influences, such as temperature or the presence of electromagnetic radiation, can change the molecule condition, resulting in a transition from one rotational vibration level to another. Visualizing the possible transitions that can occur after a molecule has been photoexcited, scientists use a powerful tool called the Jablonski diagram. The energy levels of a molecule are shown by the horizontal black lines, with energy increasing along the vertical axis of the diagram. The bold lines represent the lowest vibrational level of each electronic state, with the higher vibrational levels represented by thinner lines. Now, let's talk about the different ways a molecule can emit or absorb energy and its representation in the Jablonski diagram. Absorption is a radiative transition from a lower to a higher electronic state of a molecule. Absorption of a photon promotes the molecule from the ground state S0 to one of the vibrational levels of the singlet excited states S1, S2, Sn. These are represented by the blue arrows in the diagram. Vibrational relaxation is a non-radiative transition to a lower vibrational level within the same electronic state. After a molecule has been promoted to an excited state by absorption, it is in a non-equilibrium state and will eventually dissipate that energy that has gained and return to the ground state. It is represented by orange arrows and occurs on a rapid time scale of 10 to the minus 12 to 10 to the minus 10 seconds. Internal conversion is a non-radiative transition between two electronic states of the same spin multiplicity. A molecule in a higher lying singlet electronic state may also undergo internal conversion to a lower lying singlet electronic state, which is shown by the purple arrows.
Numerous investigations supported the idea that the efficacy of the photosensitization is directly related to the yield of reactive species of oxygen in the tumor environments, and it depends on the concentration of oxygen in the tissue. Epoxy cells are very resistant to photosensitization, and the photodynamic reaction mechanism itself may consume oxygen at a rate sufficient to inhibit further photosensitization effects.
Now that we have explored the fundamental physics behind the PDT, we can explain the mechanism function of this novel therapy, from the light absorption in the PS to the cytotoxic effects on the tumor cells. The initiating step of the photosensitizing mechanism is the absorption of a light photon by the sensitizer. The singlet excited PS either decays back to ground state, resulting in fluorescence, or undergoes intersystem crossover to the longer-lived triplet excited state. The interaction of the triplet excited PS with surrounding molecules results in two types of photooxidative reaction pathways. Type 1 pathway involves electron or hydrogen atoms transfers, producing radical forms of the PS. These intermediates may react with oxygen to form peroxide, superoxide ions, and hydroxyl radicals, which initiate free radical chain reactions. Type II mechanism is mediated by the energy transfer process with ground-state oxygen. The generation of singlet oxygen via type II pathway appears to play the central role in photodynamic cytotoxicity because of the highly efficient interaction of these species with different biomolecules. Either of these two pathways can evoke the three main cell death pathways: apoptotic, necrotic, and autophagy-associated cell death. The apoptosis pathway is morphologically characterized by chromatin condensation, cleavage of chromosomal DNA into internucleosomal fragments, cell shrinkage, membrane bleeding, and formation of apoptotic bodies without plasma membrane breakdown. On the other hand, necrosis is morphologically characterized by vacuolization of the cytoplasm, swelling and breakdown of the plasma membrane, resulting in an inflammatory reaction due to release of cellular contents and pro-inflammatory molecules. Autophagy is characterized by a massive vacuolization of the cytoplasm. Autophagic cytoplasmic degradation requires the formation of the double membrane structure called autophagosome. Autophagosome-lysosome fusion results in the degradation of the cytoplasmic components by the lysosomal hydrolysis.
Now let's start to use for PDT, the two-photon method. This standard method in PDT is to use an organic PS activated by continuous light. There are several fundamentally different approaches under preclinical investigation, involving different photophysics, chemistry, and photobiological mechanisms. In two-photon PDT, short laser pulses of the order of 100 femtoseconds with very high peak power are used so that two light photons are absorbed simultaneously by the PS. Since each photon only contributes half the excitation energy, near-infrared light can be used to achieve deeper tissue penetrations. One advantage of this is that the laser beam is strongly focused, then the activation volume is extremely small. This may be exploited to target individual blood vessels and reduce damage to adjacent tissues. The subsequent photochemistry and photobiological effects are the same as in the one-photon PDT.